This is an overview of the basic concepts of functions discussed in Math 50. A function in symbols can be written as y equals f of x, and is defined as a set of ordered pairs xy such that x is paired to exactly one y. Your x is your first coordinate and your y is your second coordinate. Now, if you are given a graph, you would know that it represents a function if it satisfies the vertical line test, which says that any vertical line passes through the graph of a function exactly once, meaning there's only one point of intersection between the line and the graph. Now, if you look at the graph of a vertical parabola, any vertical line passes through the graph at exactly one point. So it is a function. It is a graph of a function. Now, if we have a horizontal parabola, any vertical line would intersect the graph at 2 points. So if you look at the graph here, so this is not the graph of a function, because if you look at the graph, you have x paired with y1 and y2, and y1 is not equal to y2. Now, another concept of function is the concept of domain, which is simply, okay, you can, in symbols, you can write it as d sub f, and it is simply the set of all permissible values of x, meaning all the values of x, or all the numbers that you can substitute to x such that the value of the function exists. In set builder notation, we have this x such that x is a real number, where f of x is also a real number. Now, the range is the set of all the corresponding values of y. Okay, so it's the y value or the function values for all x in the domain of the function. Okay, now another concept relating to function is the concept of, okay, so for example, here we have this two sets xy, where we map, using the function f, we map the sets of the elements of x to the elements of y. So x1 is paired to y2 and x3 is paired to y1. Similarly, x2 is paired to y1. Now we know, okay, so in ordered pairs, f is represented by the ordered pairs x1 y sub 2, x2 y sub 1, and x3 y sub 1. If you notice, every x is paired to exactly one y, because you don't see an ordered pair you don't see two ordered pairs having the same first coordinate. So this is a function, or f is a function. The domain of f contains the values, x sub 1, x sub 2, and x sub 3. However, your range contains only y sub 1 and y sub 2. Y sub 3 is not there because y sub 3 does not have a pair in the x set. Now, another concept relating to functions is the concept of a one-to-one function. Basically, it is a function, so it must satisfy the definition of a function that x is paired to exactly one y. So for a function to be one-to-one, y must also be paired to exactly one x. So dapat 1 to 1. They're committed to each other. Okay. Now, by definition, another formal definition would be if y1 is equal to y2, then x1 is equal to x sub 2. To check the graph, if it is a graph of a one-to-one function, you use the horizontal line test, which says that any horizontal line must intersect the graph of a one-to-one function exactly once, meaning there has to be one point of intersection between the horizontal line, or any horizontal line, and the graph of a function. So if we look at the graph here for illustration, The graph of the vertical parabola, this is a function, but it does not satisfy the horizontal line test, so this is not one-to-one. Now, the graph of a square root function is like half of a horizontal parabola. Well, this is a function, and it also satisfies the horizontal line test. So this is a one-to-one function. Now, why is this important? Because this is a necessary condition for the concept of inverse. What is an inverse of a function? The inverse of a function, we represent it as f raised to the power of -1. It's the set of all ordered pairs x hat, y hat, such that x hat comes from the range of f and y hat comes from the domain of f. So the x and y, or the first and second coordinates of f, are just swapped. Okay? Again, as I said earlier, it is a necessary condition. The one-to-one-ness of a function is a necessary condition for the existence of the inverse, meaning it has to be one-to-one for it to have an inverse. The inverse of a function must also satisfy the composite condition. F of f inverse of x must be equal to x, and f inverse of f of x must be equal to x. Okay, since we're just swapping, so the domain of the inverse is the range of the function, and the range of the inverse is the domain of the function. Now, we can also treat functions like numbers, so we can do operations on them. Okay, so the addition of functions, again, subtraction is just addition. So if you have h of x equal to f of x plus or minus g of x, you simply add the function. The domain would just be the set of all numbers in the domain of f and in the domain of g. So that is the intersection of the two sets. Okay? There. Now, another operation that is covered in Math 50 is the concept of multiplication, where you simply multiply functions just like you multiply algebraic expressions. Okay? So, let's say, suppose you have p of x equals to the product of f of x and g of x, then the domain of p of x is still the same. It's the domain of all, it's the set of all numbers that are in the domain of f and the domain of g. So it has to be in both sets, so it's the intersection. Now, another operation is the concept of division. The problem with division is you have a denominator. So f of x over g of x. G of x must strictly be not equal to 0, otherwise we'll have an undefined expression. The domain of the function is the set contains the numbers that are both in the domain of f and g, but with a restriction: g of x must not be 0. So you have to remove all the values in the domain of g that make g 0 to avoid getting an undefined value. Okay, now there is another operation which I consider a special kind of operation, which is function composition. So it's k of x equal to f circle g of x, or you can say f of g of x, meaning the value of g, you put it as an argument into f. The domain of this would be the set of all numbers in the domain of g, such that the value of g of x is in the domain of f. Okay, so now let's discuss the basic types of functions. So one of the basic type is a polynomial, or the polynomial function is in this form: a sub n x raised to n plus a sub n minus 1 x raised to n minus 1 until a sub 1 x plus a sub o. This is a function. If a sub n is not 0, this is a function of degree n. Since there are no x's in the denominator, then the domain is a set of real numbers. Okay, so a constant is a polynomial function, which is f of x equal to c, where c is any real number. C can be 0, c can be anything as long as it's a real number. So the graph of this is a horizontal line at y equal to c, meaning whatever the x is, since you don't have an x in your function, so whatever the x is, the y is always c. This means that the range contains only one value, c. Okay, so another function is a linear function, which is of the form f of x equals ax plus b. A cannot be 0, otherwise it becomes a constant function. So the line is a slanting line. It's not horizontal because that's a graph of a constant function. Since this is a polynomial function, the domain is just a set of real numbers, and if you observe the line, it can stretch infinitely, so the range is also the set of real numbers. A is a special symbol, or it's a special value, which we call the slope of your line. Okay, now another common type of polynomial function is your quadratic function, which is of the form a squared a sub ax squared plus bx plus t, and a cannot be 0. Again, if it's 0, it becomes linear. So this is a vertical parabola because the horizontal parabola is not a function. The vertex, or the extreme, which represents your extreme point, has the coordinates hk, where h is negative b over 2a and k is just the value of the function at h. When a is positive, your parabola opens upward. Okay, so let's look at the graph. The parabola opens upward with the lowest point at a vertex. So the lowest value of y is k. This means that the range of the function is the set, or is the interval from k, including k, to infinity. If a is less than 0, we have a vertical parabola that opens downward. The highest point is the vertex, meaning your y will have a maximum point at k. So the range of the function is from negative infinity to k, including k. Again, the domain of this is a set of real numbers. Finally, for polynomial functions, we have the cubic function, which is f of x equals ax cubed plus bx cubed x squared plus tx plus d equals 0. Again, a should not be 0. Now, a cubic function is an odd powered function, or a function of odd degree. So you have two possibilities for the graph of your function, or for your function, for the roots of your function. It can have one real root or three real roots. So for a function to have one real root, the function must cross the x-axis once. So there, this is the graph of x cubed. If you have three real roots, then the function must cross the x-axis 3 times. So this is an example of a cubic function that crosses the x-axis 3 times. There. Okay, so that's it for polynomial functions. Another type of functions is a function with roots. The root function. So example would be the square root function. The square root function, represented by square root of x, the argument, or the value under the square root sign, must be positive, 0 or positive, or you say non-negative, for it to exist, because when x is negative, it becomes imaginary. So the graph of the function is like half of a horizontal parabola that opens to the right. Okay? The domain of this is the set of all non-negative numbers, and similarly, the range is the set of all non-negative numbers. Now, another common type of root function is the cube root function, which is represented by cube root of x. Okay? So, since the degree is odd, the index is odd, then it can take any possible values, because this is just the inverse of x cubed. So, the x cubed can take, the value of x in the x cubed will be retained. So, okay lang siya na mag-negative. So, this is the graph of the function, the cube root of x. And so, if you look at this, the domain is, again, is the set of real numbers, and the range is also the set of real numbers. Okay, so these are the basic for the root function. Another type of function is the, let's see, the rational function. It's like the quotient of two functions. So f of x, an example is f of x, so in the form f of x over, this should be h of x equals f of x over g of x. G of x should not be 0. Okay, so the quotient, this is supposed to be q, okay? Q of x equals f of x over g of x. So let's say an example of a quotient function, f of x is equals to 1 over x. X should not be 0, remember? Because it becomes undefined. So meaning we have asymptotes. It also, if you notice, the numerator is 1, so your y will never be 0. So we have two asymptotes, the vertical asymptote and the horizontal asymptote. The vertical asymptote, we have x is equal to 0, and for the horizontal asymptote, we have y is equal to 0. Meaning, the asymptote means that the graph of your function will get closer and closer to that line, but it will never cross or touch that line. Okay, so simply you just have to, so there, that's the graph of 1 over x. Okay, so the domain of this is the set of all numbers except 0, and the range is the set of all numbers except 0. Now another type of function is our exponential functions, which is of the form b raised to x. If b is between 0 and 1, our graph would look like this. This is less than 1, so meaning if you raise it to a positive power, the value of b raised to x would get bigger and bigger. No, it would get smaller and smaller. So, example, 1/2 raised to 2 would become 1/4. So, it gets smaller and smaller. So, this is the graph of your function. The domain, if you look at the graph, the domain is the set of real numbers. But the range, well, it's just from 0 to infinity, 0 excluded. So if you have b greater than 0, so it would be an increasing function. So the graph would somehow look like this. When x is 1, y is b, and you have the same domain and range. Now the inverse of the exponential function is the logarithmic function in the form of the logarithm of x to base b. So since they are inverses, so you would expect the graph to be a reflection with respect to the line y equals x. Okay, so one common function is the logarithm of x to base 10, or we simply write log of x. So this is how it looks like. It's just a reflection of 10 raised to x. A reflection of 10 raised to x along the line y equals x. So let's see. There. Okay. So you just compare them, the graph of b to the x and the graph of log of x to base b. Now another common logarithmic function is when the base is e, or the Euler number. So it's ln of x or ln of x. Ln of x is just the logarithmic function to base e. So basically the graph looks the same. The domain and range are the same. So here is our function.